So just like last time, this is just a short video to sort of highlight the important points you were supposed to get out of this tutorial. This slide was meant to serve as a reminder that the equation for work is a scalar, but the equation for it is dependent on some vectors. And let's say force times, let's say distance, but our distance is not really a distance, it's a displacement. We care about the distance as the magnitude that goes into the equation, but it definitely has a direction that matters for the work equation. So if you have a object, for example, that's being displaced like so, and you have a force that is acting on it this way, there is no difference between the direction of those two vectors, so 0 degrees, and therefore the force times distance times cosine theta would give a positive value for the work. We want to emphasize that we would not put in a negative value for either the force or the distance, even though they're pointed down and to the left here. We're really looking for the absolute value of the force vector, the magnitude of it, times the magnitude of the displacement times cosine theta. And since it's the magnitude of displacement, that's why so many people would refer to it as a distance. I'd also like to point out that if you have an object displacing like this and a force acts on it that is in the exact opposite direction, the fact that it's in the exact opposite direction, we can still use the absolute values for the calculation, but then the cosine theta, we would have a theta of 180 degrees. I also want to point out that it does not have to be 180 degrees to give us a negative work value. We could have a situation like the force pointed this way. The angle across here between the displacement vector and the force vector is obtuse. It's more than 90 degrees. So the cosine value will still be something negative. This will be less work than if the force were perfectly anti-parallel to the displacement. The value will come out to be a lower magnitude of work, but the cosine theta will still make this a negative value. What we're looking for, of course, with the 0 is if you have a displacement that is like this, you could have 0 work done by either having 0 displacement or 0 force acting, but what we're looking for here is what if the force is perpendicular to the displacement. The cosine 90 degrees would give us a 0. On this slide, we're given this positive point charge at the center of the slide, and you're asked to draw the electric field coming out of it. So, of course, that would be radially outward in all directions. And what we're getting at with this slide is that this charge creates a field around it, and we're asking you what would happen if a smaller positive charge was moving from point W to point X. So it's moving here. It's got a displacement in this direction. That means that as a positive charge moves from point W to point X, the electric field does positive work on that charge. In part C, it's asking if the charge moved from X to W, how would that be any different? And the answer is the displacement magnitude would be the same, and the force acting on the charge over the entire period would be the same, but the displacement would then be in the opposite direction of the force. So the work done by the field would be the same magnitude, but negative as it moves from X to W. So now that we've clarified that the orientation of displacement relative to the electric field tells us something about the work that is being done, we can see in this slide that as the particle moves from point X to point Z along that circular arc, the displacement is always perpendicular to the field lines at any point on that path. So 0 work is being done along this path by the field on the charge as it moves from point X to point Z. So this is the slide where we're sort of coming to a culmination of what all these things are supposed to mean. As a positive charge is moving from point X to point Z, we can see over here that the field will do some negative work on the charge. And then as it gets over here, the force is actually stronger because the field is stronger because we're closer to the source charge. But the field and the displacement are now perpendicular. So no work is actually being done Then on this last part of the path over here, we can see that positive work is being done because the field and the displacement don't align perfectly, but they align by an acute angle. So cosine of an acute angle would give us a positive value. The work would be positive for the second half of this path. That means that no net work is done on the charged particle as it moves from point X to point Z. First negative work is done, then positive work is done, and because X and Z are equidistant from our center charge, the path is symmetrical and the net work by the end is 0. That tells us that the path does not matter. This is a path-independent value, that the work from X to Z is 0 on this charge. And notice the last question, would our answer change if we replaced plus Q naught with plus 1.7 Q naught? No, how big our test charge was moving from X to Z never mattered in our reasoning. If we place a larger and larger charge at X and move it to Z, then the work done would still be 0. So our point is that the charge itself moving from X to Z doesn't matter. The space around our center charge has been altered by the presence of this center charge. This electric field and the potential around it do not depend on the charge that you put into the field. So to wrap all these ideas up, if the work done on a charged particle as it moves from point X to point Z is path independent, then that means I don't need to know the path it takes. I just need to know something about point X and something about point Z. That something is the potential at each of those 2 points. The potential difference between 2 points tells me the amount of work it takes per unit charge for the field to move a charge from the first point to the second point. Which brings us to that tricky equation, delta V equals negative ED. What the negative is telling you is this. If point W, for example, is at a higher potential and point X is at a lower potential, then the delta V, the change in potential or the difference in potential between them, will depend on whether you're going from X to W or W to X. The electric field around this positive charge would push a positively charged particle from W to X, from high voltage to low voltage. Delta V is final minus initial, meaning low minus high. So the electric field will always push a positive charge from high voltage to low voltage, a negative delta V. That's what that equation is trying to tell you. That's what the negative in the equation is trying to tell you, is that the direction of positive charge would get pushed if allowed to move freely. The electric field would push it in a direction of negative delta V from high voltage to low voltage. That's all it's trying to say. That's the end of this tutorial summation video, and I really hope that it was helpful.